let's pick off where we left off. So the ocean tides are caused by the moon's pull, or the moon has the most greatest effect. It's not the fact the water is pulled toward the moon, it's that the component vectors cause the inward ones that point toward the center of the Earth to squish the water out. I also posted on Google Classroom a good video explaining it. I highly recommend you watch it. Really get a sense for it. We also have extreme tides. The sun does affect the tides somewhat, and so when the moon and sun are parallel, are on the same line, they produce something known as spring tides, and you have very strong tides during that season. Whenever the moon is perpendicular to the line of the sun and the moon, our sun and the earth, the sun kind of cancels out a little bit, and so we get weaker tides that are known as neap tides. So, in Newtonian mechanics, which is what we do at high school level, gravity is thought of as a force. Once you get into higher level physics class, you learn that it has nothing to do, it's not actually a force. In actuality, the real explanation of everything is extremely advanced. For example, we're all moving at the same speed. We're all moving at the speed of light. The only thing is, we're mostly moving through time. We're moving through the time dimension. Once you get into general relativity, you find out that space and time are combined into one thing. And on the surface of the Earth, it's not really space that is curving that much. We do have a little bit of spatial curvature. It's mostly time that is extremely curved. And so what you have is if you have two objects near the surface of the Earth, if you have an object near the surface of the Earth, its time is going to fall because it will go down toward the center of the ground. It's really advanced, but we can still think of it in terms of gravitational fields. You think of gravity as a field or a curvature of space. Interaction between Earth and Moon is an action at a distance, but how can they interact without touching? Even in these lower level physics classes, we still have this important concept of field. We'll definitely go into it when we start talking about electrical fields and magnetic fields, but you can also think of gravity as a gravitational field. So a gravitational field is an alteration of space around the Earth or any object of mass, and gravitational field is an example of a force field. Again, in higher level classes, you learn that gravity isn't a force, but it's still a force once you go up the higher ones, which is weird. In general relativity, it's just a curvature of space. You're actually standing still. But then when you start trying to do quantum mechanics requires that be a force, and thus it becomes back a force. So for gravity, everything is attractive. There's no anti-gravity. So all the fields will be pointing inward toward the center of the Earth. The inward direction of the arrows indicates that the force is always attractive. The crowding of the arrows indicates that the magnitude of the force gets larger and larger and larger. Specifically, when we start learning about electrical fields, if you were to draw so many lines radially outward, and you were to draw a circle, gravity isn't the best example of a field. because it's really just a curvature of space. But whenever we go over electrical fields, so if we draw so many lines, and we imagine a circle, yeah, if we imagine a region, so if we draw a circle, the amount of lines going through it represents the strength of that field at that point. We take the same circle, we notice that as we get farther back, less lines go through it. There's technically an infinite amount of lines, but you can stop at any level you want to, and you notice that density of those lines decreases as you get farther away. If you didn't know this, inside the planet, gravity actually decreases. Why? Why would you think it decreases? Alright, so let's imagine we're on the surface of the Earth. So our equation is force is equal to some constant times the mass of one object times the mass of another divided by r squared. If we were to break this up into little tiny cubes, so each cube we treat each one as a just single point. So we're really close to this cube. So it's 4, so we take our mass, the m2, and we're now going to have lots of forces, right? Each cube of Earth is pulling on you. Now, the ones farthest away from you obviously aren't pulling as strongly down on you. I should probably be doing it the other way. The force on you. So these cubes are pulling you downward. The cubes down here aren't pulling downward as much, but the cubes up here are pulling you down very strong, right? So when you're on the surface of the Earth, all of Earth is pulling you downward. Some of them on this side is pulling you down and to the left. Some on this side is pulling you down and to the right. But since we can break this up into components, we have a down component and a left component. This has a down component and a right component. This left component will cancel out with the right component, so that all that's left is this downward force. Now let's imagine what happens if, let me rotate it, it's metric. What would happen if you're inside Earth? Well, now we have some blocks pulling you upward, while some blocks are pulling you downward. Alright? So when you get down, some of the Earth above you is going to cancel out some of the gravitational force, because we sum all these together. So when we go into the Earth, there is the ground pointing you up, and if you were in the very center, then you would have no gravity at all, right? Because all of the mass is pulling you equally in all directions. So inside a planet, it decreases to 0. This is because the pull from the mass of the Earth below you is partially balanced by what is above you. Outside a planet, it decreases to 0, not the same rate as inside. And toward infinity, meaning it'll never reach 0 unless you're at infinity, but you can't reach infinity. So the farther away you from the planet you are, it'll decrease in the shape. This is the inverse curve, 1 over r squared. So the force will decrease by 1 over r squared. But whenever you're inside the planet, gravity decreases linearly. Note that this is assuming the Earth is uniformly dense. This is not true. The center of the Earth is, I think, nickel and iron. Very dense center because all the gravity is compacting. And then we have a molten mantle and the crust, which is less dense. And also, we have pockets of molten lava that float up, bubbles. And so, the Earth isn't uniformly dense. But if it was uniformly distributed, the mass, then you would have this shape right here. Here's an interesting question.
Planes in a field. Somebody office. Planes in a field.
Imagine that all of Earth's mass was on a very thin ring. So all of Earth's mass was on a very thin surface. So a hollow Earth. How would gravity work on the surface? But it has the same mass. It would be the same. On the surface and beyond, you would not notice any difference in gravity. So, me plotting it, gravity, and this would be radius r. So it would have this 1 over r squared curve out here. What would it be like if you were anywhere inside here? Well, we know in the very center it's going to be 0 because all the mass is pulling equally in all directions. But what if you were right here? What would gravity be like right there? It would be less. Do you know its exact value? Want to take a guess? Let's think about it. So let's put you right here. So remember the equation is force is equal to G m1 m2 over r squared. So you're very close to this region right here, right? So it's going to pull you more strongly over here. However, very weakly, this mass is going to pull you down over here. It's going to be weak because of it's so far away. This is going to be stronger because you're so close. This one right here is going to pull you upward. So we're going to pull you upward here. So this region right here is all pulling you to the left. And all this region is pulling you to the right. Inside a hollow sphere, all gravitational forces cancel. So inside a hollow sphere, you would float around. Suppose you were to dig a hole through Earth to the other side and jump in. So at the top, the gravity is G downward. So you start accelerating toward the center of the Earth. As you get closer and closer to the center, we know at center the acceleration due to gravity is 0. So there will be a point in which you stop accelerating. You reach a maximum speed at the center. Once you pass the center, gravity starts pulling you back down to the center, and so you begin decelerating. And eventually, you will come to a stop. If there was no friction, and we could do a solid, and again, this is assuming Earth is uniformly distributed in its mass. What would happen is you jump in the hole, you go and start getting faster and faster until you reach the center, and then it's almost identical. You start slowing down until you reach the other side, and you'll eventually stop, and then you'll start going back and forth. What's interesting, you work out the mathematics of this example. So if you had a hole and you jump downward, it would take you about an hour to reach the other side. Now then, if you went and decided to do this, go this path, it would also take you about 1 hour to go from here to here. Any path that you cut is about an hour of falling down. This is assuming no friction, of course. You would obviously be sliding against the subsurface as you're constantly be pointing to pulled down to the center. But these small little component vectors here would cause you to accelerate because the distance is shorter. It all take about the same time. So Einstein's theory of gravitation is that there's a gravitational field is a warping of space-time by the planet. Just as a massive ball would make a dent in a surface of a waterbed, warped space-time affects the motion of other objects. You can think of it as having a rubber sheet and you put a bowling ball in it. Bowling ball is going to cause the rubber to stretch downward. And if you take a marble and put it on it, because the rubber fabric is pulled downward, the marble is going to go down the slope. You can think of it as a gravitational well. There's something called a black hole. When a star shrinks, all of its mass is now concentrated in a smaller radius. So gravitational force on the surface increases because of the force equation. When you decrease the distance, the force increases. Black holes are when the star becomes so small that the gravitational force becomes sufficiently strong that not even light would be able to escape. Anything in the vicinity would be attracted by warp space-time and be lost forever. So lights always take the shortest possible path in time. So if we have a massive object and you shine a beam of light, a laser beam, light always takes the shortest path, but because this is curved space, the space around this point is curved inward. So we can imagine this as being a grid. What happens is around this point, the grid lines are compressed. It's hard to draw. But you see that there's a compression in the fields, and so light would be bent around it. There's a certain point in which, if you were to shrink down mass smaller than the Schwarzschild radius, so it's known as Schwarzschild. So Schwarzschild radius is the radius in which if you shrink down a mass below the Schwarzschild radius, it becomes a black hole. In which case, if light were to ever, and this radius, anything with this radius is also known as the event horizon. If light were to fall below the event horizon or the Schwarzschild radius of an object, it would go and be lost forever. There's only one possible path. Technically, inside of a black hole, mathematics breaks down. Space becomes time, and time becomes space. Very advanced concept. For the longest time, we didn't know black holes existed because it comes out because of a divide by zero, basically. We have a singularity. We have 1 over r squared. That's not the right equation, but as you can imagine, as r goes down to 0, we get 1 over 0, and we get infinity. The black hole, all the mass is infinitely dense at one point. So, if you were to shrink down Earth to the size of 1 centimeter, all the mass of Earth down to less than a centimeter, Earth would become a black hole. If you were to, Earth. So Earth's radius is, so the sun is 3 kilometers. So if you were to shrink the sun down to 1.9 miles, the sun would become a black hole. 9 millimeters. So if you were to shrink Earth's mass and put it in a point that's 9 millimeters, almost a centimeter, it would become a black hole. What would happen to the Earth if the sun became a black hole? Why? What do you mean? Well, that's within the event horizon. But what is our equation? Our equation is F equals G M1 M2 R squared. So you can think of this as the mass of the Earth. Did we change the mass of the Earth? And you can think of this as the mass of the Sun. Now all we did to the Sun is take the mass and squeeze it down to a single point. But did we change the total mass? So what would happen if the Sun became a black hole? None of the above. So letting the equation for gravity guide our thinking, we can see that there was no mass changes. All we did was change how the mass was distributed. We're not inside the Sun. Alright. So there would be no change in force between the shrunken Sun and Earth. Because there's no change in mass, and our equation tells us that force would not change. Now, some solutions to general relativity or Einstein's equation of gravity allows for wormholes. So a wormhole is an enormous distortion of space, but instead of collapsing to a single infinitely dense point, it opens again in some other place. So if you could think of the fabric as being a piece of paper, this paper can be in any shape. But if we were to imagine that two faraway points, we were to stretch it out and connect them, we would be able to transverse the paper through a shortcut. We don't know if they exist, but there are solutions to general relativity, the equation, so they exist mathematically. And for the longest time, we had no clue black holes existed. We thought it was a mathematical fluke. And it was actually just this year that we confirmed black holes existed. We've known they've existed, but this year they just mathematically proved that the object in the center of the Sun was 100% a black hole. Yeah, they had a picture that helped in it. But we never had 100% concrete proof. What it was is we finally got enough measurements in measuring the object, the black hole in the center of the galaxy, to define that its radius was most definitely smaller than the Schwarzschild's radius, and its density was high enough that there's no possible explanation other than a black hole. Mm-hmm. So, universal gravitation. Everything attracts everything else. Earth is round because of gravitation. All parts of Earth has been pulled in, making a surface equidistant from the center. It's not exactly. There is rotation causing it to bulge outward. And the universe is expanding and accelerating outward. That's actually dark energy. There's a reason why it's continually accelerating. But we're not going to get into that. We're going to be looking at universal gravitation. So let's do some examples. So our equation is F equals gravitational constant m1 m2 over r squared. Where G is equal to 6.67 times 10 to the negative 11. And this is in Newton meter squared over kilogram squared. So let's provide some masses. Mass of the Earth, 5.98 times 10 to the 24 kilograms. And the radius of the Earth is 6.38 times 10 to the 6 meters. This is the Earth. How much would a 50 kilogram person weigh on the surface of the Earth? Well, we can apply F equals ma or mg. So weight equal to mass times the acceleration of gravity. You can use A for acceleration or G because it's a gravitational acceleration. So mass is 50 kilograms. We know that the acceleration is 9.8 meters per second squared. And we can see that it's 490 newtons. We could also use this equation. So force is equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. Mass of the Earth is 5.98 times 10 to the 24 kilograms. Mass of the person is 50 kilograms. And the distance between the centers, note that this distance r is from center a mass of one object to the center of mass of the other. So it would just be the radius, 6.38 times 10 to the 6 meters, and we square it. So meter squared, kilogram times a kilogram is a kilogram squared. So we're just left with newtons. And calculating it using this, we see that the mass, or the force, weight, is 489.9544 newtons. We can also compare these two equations. So we have force equals G m1 m2 over r squared. And we have F equals ma. This is the same force. We just shown it here. So what does this represent? So we have force is equal to a mass times acceleration. We have force equal to this times the mass. Acceleration. So we can let the acceleration due to gravity be equal to g times a mass over r squared. Or you could just put it as g m over r squared. So let's do that. So gravity on Earth be equal to 6.67 times 10 to the 11 Newton meter squared per gram squared. Mass of the Earth is 5.98 times 10 to the 24 kilograms divided by radius squared. So that'd be 6.38 times 10 to the 6 meters, and that'd be squared. Meter squared, we cancel out with meter squared, and kilogram divided by kilogram squared is just divide by kilogram. And so we get G is equal to 9.799088, and so meters cancel out with meter squared, kilogram cancels out with square here, so we get Newton per kilogram, which is the same thing as 9.799088. A Newton is a Newton is equal to a kilogram times meters per second squared. So this is meters per second squared. Note that the Earth is not uniformly distributed. So this is assuming that all the mass is located at a single point. The radius also is a constant. We have bumps and valleys. By the way, how smooth do you think Earth is? So if I were to shrink down the Earth to the size of a golf ball or ping pong ball, how big in millimeters do you think the Mount Everest and Mariana Trench would be? A billiard ball was the better example. So if you were to shrink down Earth to the size of a billiard ball, then the distance between the highest peak and the lowest valley, assuming you removed all the water, would be 0.005. It's smoother than a billiard ball. Earth is incredibly smooth. It's very massive, so we see the bumps very easy when we're on this scale. But if you were to go in outer space, you would not be able to see any mountains. It would look incredibly smooth. It's not round though. So it's not as round as a billiard ball, but it is smoother than a billiard ball. So 0.04 millimeters. So 4/100ths of a millimeter. You would not be able to feel any bumps on Earth if you shrunk down to a billiard ball. It would be smoother. It's saying here that, okay, maybe not. It's saying here that you would be able to. So it looks like it would be a little less. I'm just reading off of a myth. They can really measure bumps that big. But it would look very smooth at least. Maybe not as smooth as a billiard ball. So suppose we had a 1,000 kilogram block and a 50 kilogram block separated. Again, we measure from the centers by 1/2 meter. What would be the gravitational pull on each object? So this object would pull with this force, and because of Newton's third law, equal and opposite, this object would pull with the same force, just in the opposite direction. So F equals G m1 m2 divided by r squared. Because the forces are the same, it doesn't matter which m we use. So that'd be 6.67 times 10 to the negative 11. And it would be 1,050 and 0.5 squared. And we see that the force is 1.334 times 10 to the negative 5 newtons. So a very small force. That's equivalent 0.00001334 newtons. We're writing not in scientific notation. And again, 1 newton of force is the same as to lift an apple 1 meter in the air in 1 second. So that is an incredibly small force. By the way, we call this term, let me go back over here. We call this, another name for this, we can think of gravity as a field. We can also call this term gravitational field strength. Is another term for acceleration of gravity. When we call a gravitational field strength, we usually refer the units newtons per kilogram. So when we describe it as a field, we usually like to think of it in terms of a force field. So we have a force of our kilogram, but that's equivalent to a meter per second squared. So you could think of it in either way. I think that's where I'll stop today.